So could we start?
Absolutely.
So, good day, everyone. It's HSE team, and we are going to provide some overview for about the UO programming language, basic essential. And here is our outline. We'll talk about elegant objects, some information about UO, basic principles. We'll provide some examples about your centers and provide comparison of object-oriented programming language, Java, C++, and EO. Then we will provide a quick start to check and set up environments, to write simple codes, hello world, to provide some examples about Fibonacci factorials, and we'll tell you about our prospects and projects. So let's start directly, and I will pass mic to my colleague Evgeny to tell you about basic principles and paradigm of EO.
Hello, everybody. Today we'll be talking about the EU programming language. This workshop is an introductory talk, so we are going to discuss the essentials of the language and look at some basic example programs. The EU programming language is a part of the EU project, which evangelist and main contributor is Yegor Bugayenko. The language has originated from two main sources, the phi calculus and the elegant objects paradigm. Let's take a look at these notions. So the phi calculus is a model of object calculus formulated by Yegor Bugayenko as a proposition of the formal basis for the object-oriented programming paradigm and the EU language itself. The phi calculus vastly relies on the lambda calculus, which is applied in functional programming. The phi calculus defines abstraction, application, decoration, and dataization as the principal elemental operations that comprise the sufficient set of operations that can describe object-oriented programming paradigm properties and semantics. So, in other words, these four operations are the only operations that we need to build an OOP environment. We will discuss these operations a little bit later. So the elegant objects paradigm is a congregation of advised conventions to achieve proper object-oriented principles and designs in practice. The overall review of all of the principles of the paradigm will take us hours. So if you're interested in these ideas, please find Yegor's books on the yegor256.com/books. Still, let me mention some of these. The elegant objects paradigm advocates immutability of objects, which is the central idea of the language too. Also code or logic-free constructors, which means that the construction of an object should be a primitive process. In addition, elegant objects advocates pure object-oriented programming, which means no null references, no static entities, no classes, and surprisingly, no inheritance. This is an example program written in the language. We can see from this sample that almost everything is an object. In fact, everything is an object except meta declarations at the top of the file, like package or alias. There are different ways of working over objects. So it may be abstraction, it may be application, decoration, and evaluation. Yegor calls evaluation as dataization, but I personally prefer the former term, so I will be using it throughout our talk. But for now, you may have a question. What is an object? Essentially, an object is a set of attributes. An object links other objects through its attributes to compose a new concept that the object abstracts. An attribute is a pair of a name and a value, where a value of an attribute is another object. So let's have a look at this example. Factorial is an object. It has some attributes. Actually, there is no some properly named attribute. It is a specific syntax for decoration, but it has this @sign attribute, and it is also an object. So everything is in this language is an object. Attributes may be free or bound. Free attributes are inputs of an object. of an object, these are placed in square brackets, like here, n is a free attribute. I need to say that every free attribute may become bound during application when we pass actual values to the inputs. Say we can bind 10 to n, and free attribute n becomes bound. And also objects may have bound attributes by design. We can say that this @sign attribute is bound to. So we call objects that have at least one free attribute abstract, because they still have something left to be bound and concretized. And those objects that do not have free attributes are referred to as closed. So here I can say that this factorial is abstract because it has n free attribute which is not yet bound. However, at this line at the bottom, factorial n becomes closed object because it is fully applied. Now let us take a look at the essential operations over object in the language. The first operation is abstraction. Abstraction is the operation of declaring a new object. Abstraction allows declaring both abstract and closed, anonymous, or named objects. So this is very general. When abstracting objects, we do care about its inner structure. We declare inputs and outputs, and links between them. You may compare this operation with class declaration in traditional OOP languages like Java. However, in EO, there is no classes. Objects declared through abstractions are still objects. You can use them from the box, even if all or some of their inputs are not bound to some values. This is called partial application, but remember, this may lead to errors if unbound attributes are actually needed for the object to be executed or evaluated, in other terms, during runtime. So here we have this scheme where we have some input attributes that we call free attributes, and some output attributes that we call bound or bound by design. And here we defined this structure of the object, so what attributes it has, what of the attributes are free and bound, and also we define the links between them. So we say may link input A with output C in some way. This is abstraction. So it resembles a class declaration. And syntactically, it includes the following elements. A sequence of free attributes in square brackets, like here A and B are free attributes, and perimeter object does not have any. So there's an empty list of these. Also, bound attributes are placed in the body of the abstracted object. The body means the indented block. So we must put 2 space characters here so that the language knows that this is a body. Some abstractions may have a name, like a rectangle here. We put the name with this special arrow syntax. And some are anonymous, like this object. So it does not have a name, it does not have any free attributes, but it has some bound attribute, in this case, @sign, that we will talk about later. Okay, let's proceed to the application. Application is the operation of copying an object previously declared with abstraction, optionally binding all or part of its free attributes to some object. We discussed it previously. It is called partial application. So application is actually instantiation of objects in traditional languages. But here, as we talked before, all objects are equal to in this sense, even closed or abstracted. If we are to compare abstraction and application, we can conclude that abstraction allows broadening the field of concepts or objects by declaring conceptually brand new objects with their own structure. Application produces more concrete and specific copies of objects declared through abstraction by defining the actual links between the concepts by binding their free attributes. So we pass actual values, and the links that we define in abstraction work. Okay, when we abstract an object, we are its author. So we define the links and so on, its structure, inputs and outputs. And when we apply an object, we are its users, like here. While application, the object becomes a black box for us. We don't mind what is going inside. We just use the objects as a black box. And here we pass some parameters like 7, x, and 0.1, and the object gives us its outputs. Okay, syntactically, the application is quite wide and broad because it has two different syntaxes, like horizontal notation, or also referred to as infix or plane, like here A mul B bound to area, which means A times B. This is horizontal notation, object dot its attribute and parameter. This is just 2 is also an object of type int. And vertical notation, or also called inversed or prefix, is mostly used in real programs because it is actually more convenient to use it. We will talk about it later. And again, applications may be named, or top-level applications, or nested, like sprintf is an application inside another application. And basically, application has the following structure. We put applied object or copied. Here it is a rectangle. And then arguments that we want to bind to its free attributes. So we bind 10 to the first attribute A, and we bind this anonymous abstracted object directly in here in the application to parameter B. Okay, let's proceed next. I also should have talked about free and bound attributes, but we already discussed it. And the decoration. Decoration is the operation of extending one object's, we call it the decorator, attributes with attributes of the other object that we call the decorator. This may sound hard to understand first, but we'll explain it later. Through decoration, the decorator fetches all the attributes of the decorator and adds up new own attributes. Hence, the decorator represents the decorator with some extension in the functionality. Here we can see it. Here our top object decorates this smaller object, which in turn decorates this object. Because of decoration, this object now has output XYZ because it broadens its set of parameters, its set of attributes by decoration. And this top level object now has all of the attributes that are present on the slide because it decorates it hierarchically, recursively. So decoration may be hierarchical, and this is a substitution for inheritance used in traditional OP languages. Decoration in the EO programming language is very simple. It is just plain old application that is bound to the special name at sign. We call it phi because of the phi calculus. And the last principle of the language is the evaluation model. The EO programming language is declarative in its nature, and all user-defined objects has the same evaluation strategy. So let's have a look at this example. As I already said, the dataization or evaluation is the operation of computing or fetching of data laying behind an object. The dataization process is recursive and consists of the following steps. If an object is already data, like integer, float, string, when we found the data, right? If the object is an atom, atom means the object is defined in the standard library of the language or in some other source, so outside of your environment. Atoms may have their own evaluation strategy, so they may have return data. And lastly, if the object is user-defined, it cannot return its own data. It can only turn this responsibility to its decorator, like here. We ask this top-level object, give me your data, please. It doesn't know which is data, but it knows that it has its decorator at sign. And it asks this decorator for data, and so on, down to the atoms or data objects. If in this hierarchy there is no data object or atom, this object may not be evaluated and the program will fail. Okay, so now I turn off my mic.
Thank you so much, colleague. In order to continue, I'd like to present the comparison of operators and expressions. As shown in the slide, there is a comparison between EOLang, Java, Groovy, and Kotlin, the main operators and expressions. It is interesting to say that, as it's shown, it more looks like a functional one in EOLang. So even as Evgeny said before, the code that we write in EOLang always looks like more in functional style. Well, the next slide, please. In this slide, we can see the comparison of declarative statements. This means, like, as it already said Evgeny, but it would be more visible for you to understand the difference. Well, how does it like, how to declare the statement EOLang in comparison with Java, Groovy, and Kotlin. So as we see, we just like put hello world in some object, and after that, if you want to use this, it will be like a bounded one. So, and the next one, please. Well, comparison of data types. Also, as it was already said, EOLang environment doesn't support like data types as it's used in other languages like Java, Groovy, and Kotlin, but it means like to get the information about the atom from some side environment, so the outside library or somewhere in runtime. That is why this is like a feature of EOLang. The next one, please. Well, the comparison of OOP principles. Abstraction in EOLang, this means like objects are elements into which the subject area is decomposed. According to West, objects as abstractions of real-world entities are dense and integral clusters of information. Inheritance in EOLang, this is like an implementation. Inheritance doesn't exist in EOLang. As such, inheritance contains the structure and behavior of superclasses, and this can lead to subsequent development difficulties. Also, changes in the superclass can lead to unexpected results in the derived classes. Also, in EOLang, inheritance is implemented through an object hierarchy and can be created using decorators. Objects in EOLang inherit only behavior while they cannot rewrite it, but only add new some functionality. Speaking about polymorphism, there are no explicitly defined types in EOLang. The correspondence between objects is made and checked at compile time. ELN always knows when objects are created or copied, as well as their structure. By having this information at compile time, you can guarantee a high level of compatibility among their users' objects. Encapsulation. The inability to make the encapsulation barrier explicit is the main reason why ELN doesn't hide information about the object structure. All attributes of an object are visible to any other object. In ELN, the main goal of encapsulation is the reducing the interconnectedness between objects is achieved in a different way. Also in ELN, the density of the relationship between objects is controlled at the assembly stage. At compile time, the compiler collects information about the relationships between objects and calculates the depth for each relationship. The next slide, please. And Joseph, you're welcome.
Thank you, Vitaly. Okay, so I'm going to walk you through a quick start setting up an environment. So to start with setting up an environment, first you need to clone the EO repository to your local machine. And with this, you need to have get installed. So use the command as described in the slides here, get clone, you get it onto your desktop, and then you switch directory to the EO directory on the local machine. And this example has been depicted in the picture here. Next slide, please. Next slide. Okay, all right. So the next step is to compile the transpiler and the runtime of the EO programming language. With this, you need Maven version 3.3 or above and Java SDK 8 or above installed. Then you can use either mvn clean install command, or you can use mvn with this option, the skip test clean install. This option is going to skip the test. With the first option is going to apply the test to it. So we can use either of this to compile the transpiler in the runtime. With this, you need you only have to run this once. You don't have to run it again because it's going to install the transpiler and runtime to your local machine. And subsequently, you can compile and run programs without repeating this command. So this has been shown in the picture as. Okay, so the next step is to compile the code in the sandbox. That's where we have all our examples. So we can switch to the sandbox directory with cd sandbox. In the sandbox, we have two directories. We have the canonical and then we have the HSE. The HSE one is what the HSE team has built. So you can go to the HSE directory in the sandbox, and then you run the mvn clean compile to build the examples in that directory. And the result is what's been depicted in this picture here. Could you move to the next slide? So as an example, we can run a hello world program as this. So we have the code, and as my colleague Evgeny described the syntax of EOLang earlier. So you can have like a hello world program written like this as shown here, and then you can compile with mvn clean compile while you're in the HSE in the sandbox directory. And after compiling, you can run with run.cmd if you're on a Windows laptop, or you can use the run.sh if you're on a Mac or a Linux machine. So that's it for a hello world program.
And now let's see some examples of programs. Could you please ensure that all of my screens are visible? So here's my IDE and here's my terminal, right? Can you see this? Because
okay.
Okay, yeah. So let's look at these examples. Here we can see a basic program that finds a factorial of n. The factorial object is defined through abstraction, as we can see, because of these square brackets. It has the n3 attribute as its input. It does not have any output bound attributes, except the special add attributes, which we now can tell is used for decoration. So, however, the factorial is decorating a complex object if, as we can see. We don't really need to superset the attributes of if. Instead, we use decoration here because the calculation of the factorial should be delegated to the if objects. This is basically how we write programs in EU. We construct objects and delegate their evaluation to other objects. This deep hierarchy is terminated on the level of atomic library objects, as we discussed previously. If is a quite complex object. You may be disoriented because of its multi-linity of this syntax. However, vertical notation, which is inverse, helps us here to focus on important things. Let me rewrite this application to the horizontal notation to see this. So if is an attribute of less, because this dot means that the next object is the owner of this one. So if is an attribute of less. So I type less. Less in turn is an attribute of n. So it becomes like this, and less something. In this case, and less 2. This is our object. If, and then if has its attributes 1 and this complex product. So I type 1, and mul is an attribute of n, and mul factorial, and we pass to factorial this difference, n sub 1. So this is the horizontal version of the, ignore these lines, this is the horizontal version of this application. It has some issues. We don't, it is quite not easy to comprehend, and it is quite messy and harder. Yeah. So vertical notation helps us here to focus on programs and on the main elements and make the programs more clear. So let's take it back. And now we see the more practical things. So the factorial is an if. If n is less than 2, like we can see here, then the answer is 1. Instead, the answer is multiplication of n and factorial of n minus 1. So the program is can be read natively. This is much clearer and looks like the original mathematical formula. App factorial is a special object that consumes arguments from the console. This syntax means that vararg, variable length attributes. And let me run this object with n equal to 10. So I copy this, go to my terminal, and pass the name of the object and argument, and it computes. Okay. And now let's look at this example. This is the tail recursive factorial. It is just the same, however, it is based on the tail recursion. Tail recursion is a type of recursion where we pass current answer as one of parameters of the recursive function. Some languages may optimize such recursions to basic loops for better performance. As we can see, factorial has inner subfactorial. This is done to get rid of the need to pass the initial value of accumulator for the client of factorial. So I defined subfactorial to get rid of this one. So the user of the parent factorial tail does not need to pass something because it is not idiomatic. User may pass wrong value or forget to pass it at all. The subfactorial is the same. We just pass the answer as one of params. So if n less than 2, then the answer is already done. Instead, we call the subfactorial with the current answer passed here. So it is just the same. And let's run this program as well. with 10. So it works. Next, okay, now that we discussed basic recursion and tail recursion, let us apply this knowledge to arrays. Here with some elements of an array R. This is a plain simple recursion. As we can see, we don't pass the current answer to as one of the parameters. The base of recursion is this line. So this is the base, these two lines. If the current n is greater or equal, gec means greater or equal to the length of the array, then stop. The recursion should be stopped. The sum of the empty array is 0. This value is used as a terminating addend as well. When the array is not done, add current element to the sum of the orders. So pretty straightforward. So let's run this one as well. With 1, 2, 3, 4, 5, for example. Oops, it's not that object. I need to run app sum rec, not sum rec. And here it works, 15. And now let's take a look at another approach of working with arrays. For this, we have standard library functions, reduce and map. Reduce is used to collect n elements of some array into the only one aggregated value. Sum is a perfect example for this operation. Here we call reduce attribute object on the R object, which is an array. Pass 0 as the initial value of aggregation. We refer to it as an accumulator as well. And then we pass a special reduce object, anonymous reduce object, which knows how to aggregate the current value with the current accumulator. Here, this is just an addition of the two because we want to find the sum. The reduce library function just slides the array from the first to the last element and performs the aggregation, or folding as people call it in functional programming, just as we commanded it to do through our special reduce object. Okay, let me run this app again. It's also 15. To demonstrate you the map operation, let's have a look at this simple object that we actually used here to print str r to int r. But I haven't mentioned it before. This object is used to turn any array into an array of strings. It is done through the sprintf object here. Sprintf object works just like sprintf in C or string format in Java. It takes the format string that may have placeholders and format parameters like precision of numbers and other things. And here we map through the original array and turn it into the array of string objects that we brought from sprintf. Map is just end-to-end operation. It turns n elements to n elements with some change. Like here, we turn some type, we don't know it yet, to strings. Int r to str r that we used delegates its evaluation to the more general r to str r by passing this integer number format to it. Okay, so we have discussed some basics of the language. Now the conclusion part. Thank you for your attention.
Thank you very much. Could you please open online presentation, Shania?
I already have.
Next, we have updated it. Online.
This is the online version. Okay, let me just reload then.
Okay.
So it's the last slide. Oh, no, not the last, but the conclusion, yes?
Next one. Future work, next one. Number 28. Yes. So we have a question. Can we build a serious application using EO language? To answer this question, since we have limited time, we have provided some examples. For that, we have implemented JPEG model using TO. It is a tool that designed to analyze code quality by measuring cohesion and some metrics. This model built into our pipeline JPEG tool, and now it's called the EO JPEG. You can check it by the link. Second example, it is to implement series algorithms to check work with graphs like Dijkstra, Prim, and Kruskal Falstron algorithms, and we have implemented them. You can find them in by the link provided, and we have analyzed design patterns in EO. Can we build some pattern in EO? So we have built some examples. You can find by the link, and just we can share with you a simple tutorial how to work with this language to set up, implement the basic example, and others. You can find by the links. It's all, and thank you very much for your attention. Igor, maybe you can add some words to our presentation.
No, I like what you said. It seems pretty accurate description of the language. And many thanks for your contribution, the development of it. So that's it.
Thank you very much for your team. So I will share this presentation in our group. We have to update some links, and after that we can share this presentation with references in a Polystat group, and hope we can continue to work on our book. All the best, and thank you very much for your team. I suppose, as I promised, it is 50 minutes, and we got it. Thank you very much.
Thank you.